Okay, hi everybody. Yeah, I'm Driss. I work at Meta. I've been working on PyTorch for about 4 years now. Today I'm going to be giving an overview of how to use some of the new floating point formats you may have been hearing about on the latest hardware with PyTorch. At a high level, if you were to store your high precision FP32 tensor and let's say FP4 directly, you'd simply lose too much information, right? You'd had 4 billion real numbers used before, and now you only have 16. So one critical technique for preserving accuracy when using these formats is called scaling. And at a high level, the idea is pretty straightforward. We're going to store a high precision tensor as two components. One is the low precision tensor, so this is FP8, FP6, FP4, what I'm going to call FPX, and some set of scale factors. And those are often commonly stored as tensors as well. And why do we do this? Well, we do this to minimize the loss of information, right? And so we use these scale factors to map the dynamic range of your high precision tensor onto that of the FPXD type. Okay, so let's look at a few different ways and a few popular strategies for doing this scaling. There's two popular strategies and scaling recipes here. On the left, we have something called per-tensor scaling, and on the right, we have something called per-row scaling. These are both supported today on MI300 GPUs and newer in PyTorch. There's going to be some diagrammatic conventions for some of these weird pictures. The gray bubble here is a window or tile. And this window or tile is the granularity by which we apply scaling. So let's first look at per-tensor scaling, because this is probably the most simple to understand. So we look at this window, and we span it over our input tensor. In this case, the window would be size m by k. Right? And this is what we're going to calculate our scale over. And how do we actually calculate this scale? Well, we first take the maximum of all the elements in the tensor along this window, and then we take the absolute, first we take the absolute values, and then we take the maximum, and we call this the A max. And then we take whatever FPXD type we're going to store to, and we take the maximum representable value. So for something like FP8, this would be 448. So it's a big number, but it's not that big when it comes to actual tensor data. And then we take that FP8 max representable value, and we divide that by the Amax we just calculated, and this gives us our scale. We multiply that scale by our input tensor, and this essentially maps every element in the tensor to cover the full range of this FPXD type. And then you can do what you're used to, the tensor.to FP8, and you just directly cast. For something like per-row scaling, kind of as the name suggests, we're going to change the window and how we map it onto the tensor. And we have one window per row. So in this case, our window size would be size m. And we're going to end up producing m scales, right? And ultimately, this gives us more total scales. And empirically, this reduces the impact of outliers. And this leads to lower reconstruction loss. Something to note, in both of these cases, the scales are stored directly in float32. And the low precision data is FP8. And in the new formats, this is where it's going to change. So you may have heard about MXFP8, MXFP6, MXFP4 for GPT OSS. And again, these are all supported today in PyTorch on AMD. And instead of using one scale along a given axis, like per row, we're now going to split the rows up into subtiles or blocks. And for the specifics of MXFP recipes, the size of these blocks is 32. And instead of storing the scales in float32, we're going to use this new D type that's supported in PyTorch called E8M0. It's a weird acronym. It's really just powers of 2. And that's it. And then for these MXD types, they're parameterized, right? So there's MXFP8. That means the low precision tensor is FP8. There's MXFP6 and MXFP4. Again, all supported in PyTorch today. OK, so this is a video. I made some nice pictures. I'm more of a visual learner, so I made this animation to kind of describe the differences between these scaling formats. This video moves a little quick, so we'll see how it renders. Again, you have your high precision tensor. Let's say it's bfloat16. This can be an activation or a wait. And then we have per tensor, per row, and per block. And we span a window across the input tensor. And then we calculate the maximum of the absolute values in that window. And as you can see, per block, this is more scales. So again, empirically, this is going to lower the reconstruction loss. And these are currently the A maxes we've calculated across the window. And now we calculate our scales. So in this diagram, I'm using an FP8 as our conversion type. Now we have our scales. We broadcast them to every element in the window. We multiply them or scale the tensor. And this effectively stretches or squishes the input elements to map onto our low precision data type. Wow, I can't believe I nailed that on timing. That was a quick video. Okay, cool. I talked a lot about scaling and why you would use these formats. But as of right now, I've told you you lose information in this process. So you might be asking, why should I even use these? And the primary benefit is just dramatically increase compute throughput on newer generation hardware. Right? So for FP8, you have 2x the performance over bfloat 16. For FP4, this is up to 4x the performance. And specifically, to actually do work on these and to actually capitalize on these low precision formats, you need a specialized matrix multiplication operations to use those and consume them. So this is where PyTorch's new public scaled MM API comes in. It lets you express your quantization recipes, i.e. your scales or your data formats and your layouts. And then we automatically match it to high-performance GEMM kernels. And they're optimized for the specific hardware you're operating on. And the beauty is that we can essentially hide all this complexity behind a nice high-level API. You describe what you want, and PyTorch handles the routing to the right kernel. And while it's not shown in this slide, we also have a low-precision scaled grouped GEMM, which is important for the new mixture of expert models. And yeah, so that's basically it. I'm going to hand it over to Jeff, who's going to talk about some more of the integrations we have in the ecosystem.
Hi, everyone. I'm Jeff. It was kind of a long introduction for my bio, but really I'm the AMD maintainer for PyTorch. I do dabble in more of the ecosystem of PyTorch, some of the extension projects, and I also dabble in other software that's managed by the frameworks team that I'm a part of. But think of me, I'm the PyTorch guy at AMD. All right, so we're going to talk about, well, really, me as the PyTorch guy, all roads lead to PyTorch, really in my day-to-day, customer problems, user problems, somehow it always ends up back at PyTorch. Similar to the last slide, thank you, Driss, for the introduction, all roads do lead to GEMMs. So that's really the most important kernel that we can develop and optimize on our hardware. So it took a while for industry to arrive at a consensus for how to represent at least 8-bit floating point types. Starting with the MI300 series, CDNA3, we had the FNUZ data type. And really this has a wider dynamic range. It sacrifices infinity and sign 0. This didn't take off. Instead, the Open Compute Project definition for FP8 is now the industry standard. And you can see that in the history of our GPUs as we release them. So RDNA 4 now adds support for the OCP data type for FP8. And then moving forward with CDNA 4, this is the MI355 series, the OCP standards body has now added the MX data types as well. So this is our first AMD hardware that supports all of these data types. Now, if you're trying to write HIP kernels, the low precision docs is that first link in the slide. It's an excellent reference. It describes everything from code examples, references, how to write kernels to be flexible for either the FNUZ or OCP type if you're using F8, as well as the intrinsics and helper functions that we have for creating the MX types. So a quick note on scale types. Driss mentioned E8, M0. This is the standard scale type as part of the OCP standard. And this is the one that the MI355 uses. MI355 does not support any non-standard type for that scale factor. But I want you to be assured that in the PyTorch CI, in the unit tests that are running every time that there's a commit to PyTorch, we do have MI355 supported in CI today. You can go out to the HUD for PyTorch CI and see it running. The important thing there is all of the unit tests are passing using the standard MX FP8, FP4 with the E8 M0 scaling factor to the same accuracy standards as the non-standard scaling factor. Now, I say that this is all happening live, so if you went and looked at the CI results right now, you'd see some things that are failing. And that's because, as Driss mentioned, this new public API for scaled MM is going through some changes. And so we are actively fixing anything that's broken. You're on this journey with us, and it does work, I promise. All right. If you are not interested in, if you want to write low precision GEMM kernels or any other kernels using low precision, you have to take advantage of the matrix cores in our hardware. And there's really two options for you to do that. You could use intrinsics. If you want to get really down to the assembly and you want to call intrinsics, we do have a utility for you to look at. There's a link here on the slide for the matrix instruction calculator. That is supported up through MI300 right now. The author of that tool is working on MI350 and MI450 right now. And so stay tuned for those instructions. If that's really too complicated for you to develop these HIP kernels, might I recommend composable kernel? Now, I failed to put a link on the slide, but if you just Google it on GitHub and the ROCm organization, you'll easily find composable kernel. I think CK is a great option because although it can have a bit of a learning curve, the project contains numerous examples that compile and run. Besides the MX example, which I have a link for on the slide, there are, I think today, 68 different examples of the things that CK can do, not just for MX types or low precision data types, but really for writing high performance HIP kernels. Some examples that CK can do, it can do GEMM fusions with bias, activation, group GEMM, batch GEMM, reductions, pooling, convolutions, and a lot of different operators that are important. When it comes to getting the best performance out of CK, experimentation is key. CK templates have a lot of different tuning knobs that you can use for specific your tensor input shapes to these kernels. And it does take some effort to tune it correctly. But to this end, CK does have a profiler that can help you find those right parameters as part of that project. If you're willing to put in the effort to write CK kernels and get the best performance, it really does pay off. So as a real example, we integrated CK-based GEMMs into PyTorch. You can find the code there today. We have specific heuristics for picking the best implementation, the best kernel for the CK-based GEMMs, and we tuned it for the Llama models. And doing that, we outperform using the ROCm library HipBlast LT GEMM implementations, which are generated assembly kernels. So there is really a benefit to using CK, and I would encourage you to learn how to use it. Now, if you're looking for a different approach than writing native HIP kernels, whether it's CK or just HIP directly, maybe Triton's for you. I think perhaps in this audience, many of you have heard of Triton already, but just for a quick recap, Triton is a Python-like language for writing GPU kernels. You would write your function with respect to operations that are blockwise, between blocks, et cetera. And the Triton compiler will then just-in-time compile your function into a GPU kernel. So this does remove a lot of the complexity of writing GPU kernels, and this is one of the strengths of Triton. Easy to write fusions. Performance is competitive with natively written HIP kernels. And Triton is one of the core technologies behind PyTorch 2.0's Torch compile. So if you haven't learned it yet, I really recommend diving in. One recent success, success that I would like to talk about is for the GPT OSS launch. Now, I think GPT OSS has been covered very well already today, but just to re-highlight, it's an MOE model with MX FP4 weights and bfloat 16 activations. And I wanted to bring this up because the computation, the matrix cores that are going to be used for this model, they're not in MX FP4, but that doesn't mean it's a waste, right? The benefit of using these quantized small low precision types is not just compute, but it's also space saving. And so by utilizing these quantized weights with a mixed input GEMM of MX FP4 and bfloat 16, you can still get a benefit. And that's why you're seeing GPT OSS running on a platform like Strix Halo, right? It might not have the FP4 matrix cores, but you can still run a model like GPT OSS on a wonderful platform. So this mixed GEMM implementation that I keep talking about, this was done in Triton. Now, Triton can already do upcasting of some of these mixed precision GEMMs, and so it was doing that for us when we first wrote the kernel. the MX FP4 was being upcast, but it was doing it in an inefficient way, but that's where our Triton compiler team got involved, and it went from something like 40 plus instructions for that conversion down to around 20. And I think there was one bullet on the slide today for GPT OSS that talked about improving the GEMM performance, and this was the improvement. Our engineers, our Triton core engineers, are actively trying to make Triton fast. And what I mean is you can actually today, in a lot of cases, get better performance using Triton than writing a HIP kernel from scratch. It's kind of nice at AMD. I mean, we're all one AMD, but we're just learning from each other. The CK team, the Triton team, the backend compiler, we're all working together to make every way that you want to use AMD hardware fast. Another success I do want to talk about is the June launch for MI355. All of those models were FP4, and so that's matrix core, FP4 multiplication. If the kernel was compute bound, it was using either an assembly kernel or a CK kernel from the ADER project. If it was a memory bound kernel, then it was using the Triton implementation. So it needs to be said, though, that similar to CK, getting the best performance out of Triton can be as much of a challenge. There are some tuning knobs for using Triton as well. But our engineers right now are focused across the board, across the ROCm stack, on getting the best out-of-box performance and experience. So I hinted at it at the last slide. During the VLLM talk from Simon, there was one slide mentioning ADER. But ADER is our AI tensor engine for ROCm. So when it comes to operator performance, we wanted to put our best and our brightest in one place for all users and customers. So as an example, flash attention v3, it's not just baked into PyTorch and then you have to use PyTorch to get it. It's actually implemented in ADER, and then PyTorch turns around and imports ADER, and that's how you get access to this very fast operator implementation. The list of operators that ADER supports is not exhaustive on the slide. We have multi-head attention, latent attention, paged attention, RMS norm, layer norm, rope, quantization, and the list is longer than that. What you get is the ADER developers, the kernel developers, are providing the best implementations with the tools that they have, whether it's CK, whether we have some wizards writing assembly, or whether it's CK. What it means for you as the community, as the users of ADER, you just find the operator that you need, and you can integrate it into the project that you have. And we've done a lot of that integration already in VLLM and in PyTorch, SGLang, and more. You can also use ADER as a resource. So I've highlighted CK and Triton as a means of writing low precision data type GEMMs and other kernels. You can use ADER now as a resource, right? The code is all there, it's all available to you. You can go look at the code, figure out how to write Triton kernels, figure out how to write CK kernels. It's just another resource for you as the developer community to learn how to write these kernels. Now, if you're not interested, I know I've talked a lot about writing these kernels. If you're not interested in writing your own, maybe your use case is you just want good out-of-box experience. Perhaps using VLLM is a good option for you. It's been covered in detail already today. We do have public Docker images. The latest one already supports FP4, MI355, GPT OSS. I mentioned it, we don't just put out Dockers. I know it's kind of our bread and butter. We ship a lot of Dockers, but everything we do at AMD goes open source. We're not just making one little Docker image that has some secret environment variables and then we're just handing it to you. Everything we do goes open source first. Everything is upstreamed. We are not just keeping something hidden behind the scenes. So what can you do today? So I've highlighted a few ways that you can write kernels. If you want, use CK, use Triton, use popular models right out of the box with day zero support. Places where we could use your help is just getting in there and using it, because we as the developers don't always know the corner cases that you're going to experience. Documentation, as an example, tends to be a sticking point. This new scaled becoming a public API within PyTorch. It's not in Torch 2.9, it's going to be in PyTorch 2.10, or you can get the nightly wheels available at pytorch.org. Help us develop that together. Use it. That's the big ask. We are building this together. If you're inspired to try something based on this talk today, please go out and do it. If it doesn't work out of the box, you have to let us know. Don't just go tweeting at Lisa. Find us, the developers. My name is my GitHub handle, Jeff Daly, on PyTorch. AMD is not just sitting in ivory towers working on clandestine customers to get them the best performance and leaving everyone else behind. That's not our model. Years ago, we were doing open source, claiming open source, and we always have been, and we've embraced it. But that meant we were just taking the code that we were writing and kind of throwing it over the fence and calling it open source. As Anush was pointing out today, really ROCm is changing. It's an ethos, it's a mentality. We are embracing the developer community. Your build is our build, okay? We're doing this together. Together we advance. Thank you.